In this video, we're going to do just a quick refresher about the dot product. We sometimes also call the dot product the inner product. So just to remind you, let's say we have a vector u whose components we'll write as u1, u2, up through u sub m. And let's suppose we have another vector whose components are v1 up through vm. It's going to be the convention in this video and really throughout our class that the vectors themselves will belong to the Euclidean space Rm. So the way the inner product or the dot product is defined is we simply take the sums of the products of the terms, corresponding terms. So u1 v1 plus u2 v2 up through vm. So the dot product is always a scalar. So just for example, let's say u was the vector, let's work in R3, 1, 0, 2. And let's say v was the vector 2, negative 1, 3. Then u dot v would be 1 times 2 plus 0 times negative 1 plus 2 times 3, and that works out to be 4. So some important properties of the dot product. Well, the dot product is commutative. So if u dot v is 4, so is v dot u. Also, the dot product is what's known as a bilinear operator. So let's say I take something like 5u and dot it with 2v. I take the inner product of these two. Then the bilinearity property says that we can factor scalar multiples out of the entire quantity. So in other words, this would be 5 times 2 times u dot v, which would be 10 times 4, which would be 40. Now, one of the convenient ways of viewing the dot product, and we'll be doing this throughout the semester, is to think in terms of the transpose. To just remind you what a transpose is, let's say we have a 2 by 3 matrix. The transpose is what we get when we interchange the rows and columns of the matrix. So for example, here we have an entry in row 1, column 3 of A, which is 3. So that means in the transpose, the entry of row 3, column 1 will be 3. So if A is a 2 by 3 matrix, a transpose would look something like this. Now, vectors can be thought of as matrices with one column. So if I take U transpose, it would be 1, 0, 2. V would be 2, negative 1 to 3. So another way to express the dot product is to use the language of transposes and matrix multiplication. So in other words, u dot v is u transpose, the vector u transpose times v. U transpose is 1 by 3, multiply it by a 3 by 1, you get a 1 by 1. 1 times 2 plus 0 times negative 1 plus 2 times 3. This again would be 4. So this is a convenient way of writing the dot product is in terms of matrices and transposes. Just as a reminder, if we have a unit vector and if we divide it by its length, that would be the vector or the column matrix 1, 0, 2. The length would be the sums of the squares of the components, the square root of that. So the length would be 1 squared plus 2 squared, which is 5. Take the square root of that. 1 over root 5. So now we've taken that vector, u, and we have a unit vector which is parallel to it. Okay, so that's the process of normalization, as we call it. Some other properties of the dot product. If we take u transpose u, we know that that is u dot u. And u dot u, if we take this vector u, and if we dot it with itself, we actually get 5, which is the length of u squared. So u transpose times u is the length of u squared. And it's important to realize then that if u is a unit vector, u transpose times u would be the length of u squared, which would be 1. Some other properties. Let's say two vectors have a dot product which is 0. When that happens, we say that u and v are orthogonal. We can also use the word perpendicular, but orthogonal is sometimes a little bit more common. Okay, it's also the case that if we dot u with itself, if that works out to be 0, then that means the length of u squared is 0. But the length of u squared is just the sum of the squares of the components, which is that. So if this quantity is 0, and if all of these quantities are numbers raised to the even power, that means the only way that this expression can be 0 is if u1 up through u sub m, if those are all equal to 0. And if that happens, that means all the components of the vector u are 0, which means that u is in fact the 0 vector. Let's take a look at an interesting example involving 3 vectors. And this is leading to what we're going to be looking at in depth later in the class. So I'm going to have a vector v1, which is 1, 1, negative 1. v2 is going to be the vector 1, negative 2, negative 1. v3 is going to be the vector minus 1, 0, negative 1. So these are vectors now in R3. Now each of these vectors is orthogonal to one another. So for example, let's take the dot product, the inner product of v1 and v2. This is a 1. We would have 1 times 1 plus 1 times negative 2 plus negative 1 times negative 1, which is 0. So v1 and v2 are orthogonal. v1 and v3 are orthogonal, as are v2 and v3. So these 3 vectors, they are pairwise orthogonal. Pairwise means that if we take any pair of the 3, the inner product or the dot product is 0. Now let's take these 3 vectors. Let's also form a matrix whose columns are those vectors. It's pretty easy to show that if we row reduce this matrix, we get the 3 by 3 identity matrix. You can check that on your own. And because A is row reducible to the identity matrix, we know then by the invertible matrix theorem that the columns of V1, V2, and the column vectors V1, V2, V3, we know that they form a linearly independent set in R3, and we know that the span of the three vectors is R3 itself. So in other words, the three vectors V1, V2, V3, they form a basis for R3. And they're not just any basis. They are what we call an orthogonal basis. Now we could easily take each of these three vectors and divide them by the length. So if we were to take the first vector and divide by its length, we'd be taking the sums of the squares, which would be 1 plus 1 plus 1, 3. So we'd have 1 over square root of 3, 1 over square root of 3, minus 1 square root of 3. So this is the vector. It's a unit vector, which was obtained by taking the vector v1 and simply normalizing it. u2 would be what we get when we normalize v2. So if we square 1, square 2, square 1, we'd get 1 plus 4 plus 1, which would be 6. So we're going to divide each of these by the square root of 6. And we could do the last thing with v3. We could divide each of these entries by the length of v3. The length of v3 is going to be the square root of 2. So we'd get a third vector, u3, which would be minus 1 over root 2, 0, minus 1 over root 2. So v1 and v2, v3, they formed an orthogonal basis. u1, u2, u3 they form what we call an orthonormal basis. Orthonormal means that each of the vectors is orthogonal, and the normal part indicates that each of these is a unit vector. And we will be talking about orthonormal basis quite a bit more. So here's an exercise for you to do outside of class in preparation. Let's work in R4. So u1 is the vector 1, 1, minus 1, 1. 5, 1, 3, negative 3. Let me just check that u1 and u2 are in fact orthogonal. I'd have 5 plus 1 is 6, minus 6 minus 3 minus 3. So these two vectors are indeed orthogonal. The next vector is going to be 1, negative 2, 5, 6. And the last vector is going to be 1, 2, negative 2, 0. What I would like for you to do is I would like for you to verify that these vectors are pairwise orthogonal. So that means you're going to have to take the dot products, the inner products of every distinct pair of these vectors and show that it's 0. So that would be 4 choose 2, which is maybe 6 different possibilities, I think. And then verify that the vectors u1, u2, u3, u4 form a basis for R4. That will be a simple calculation using putting these 4 vectors into a 4 by 4 matrix and showing it's row reducible to the identity. Okay, so please do that in preparation for class.